In order to analyze any equilibrium scenario that involves torque and forces, the first thing you want to do is draw a picture of your object as well as a free body diagram showing the forces acting on the object. So we have gone ahead and have done that already. We basically just copied the forces that were present in the original picture, but we've also included a couple of forces that were not shown. So for example, you have the man standing on the plank. We have shown his gravitational force right here being exerted downward on the plank. And then we also have the gravitational force or the weight of the plank itself. And that acts, notice, at the center because the plank is uniform. Most of these questions involve uniform objects, so their weight will be located in their geometrical center. So those are all of the forces that we have acting on the plank, in addition to the ones that were already drawn, the tensions. The next thing you want to do is you want to select a pivot point on your object. Now you could theoretically place the pivot anywhere, but the most strategic location is going to be at the point on your object where the greatest number of forces, or excuse me, the greatest number of unknown forces is passing. So if you look carefully, the greatest number of unknown forces is passing through that point right there. We don't know T2 and we don't know T3, so this turns out to be the most strategic selection for where the pivot will be placed. The third step is to note that because this plank is in equilibrium, then the sum of the torques is equal to 0. Now, we're only going to have to deal with 1, 2, 3 torques. We don't have to worry about T2 and T3, and the reason is that they pass through the pivot, so they do not produce any torque. Think about pushing on the hinge of a door. If you go up to a door and push on the hinge, it's not going to rotate because you are applying a force at the pivot point. It's the same idea here. So T2 and T3 will not produce any torque. We only have to deal with the 3 torques or the 3 forces that we've highlighted. Now, let's furthermore recall that torque, just in general, is equal to a force times the sine of an angle times the distance from the force to the pivot. So we're going to be using that equation for our analysis. And finally, recall that if a torque causes a clockwise rotation, it's considered negative torque. If it produces a counterclockwise rotation, then it's considered to be positive torque. So putting this all together, let's go and analyze the 700 Newton force first. Now, if you notice it's pressing downward, that would cause the plank to rotate in a clockwise fashion around the pivot. Therefore, it's going to have negative torque. So starting out with that 700 Newton force, we're going to have negative, and then we put in the force of 700 newtons times the sine of an angle. Well, look at the angle between the 700 Newton force and the plank, and you should see that it is a 90-degree angle. And then times the distance from that force to the pivot point, we can see from the diagram that that's half of a meter. Moving on to the weight of the plank itself. We were told in the question that the plank is 30 kilograms. So what we did is we took 30 kilograms and multiplied it by 9.8 meters per second squared. That's where the 294 newtons is coming from, just in case you're wondering. That also is causing a clockwise torque. So you're going to have minus, and then you put in your 294 newtons times the sine of 90. The angle between that weight and the plank itself is, again, 90. And then multiply that by the distance from the weight to the pivot. That's going to be 1 meter. Remember, the weight is located at the center of the plank, so the distance to the pivot would just be 1 meter. And then we have T1, which is pulling kind of up and to the right. A little bit tricky to see, but if you pulled up and to the right on the plank, that would cause it to rotate in a counterclockwise fashion. So that will be positive torque. Let's clear this out here. So we're going to have a plus sign, then we have the unknown force of T1 times the sine of the angle. Now, what we've done is we've extended the plank to the right, and we can see that the angle between that extended line along the plank and the force itself is just the 40 degrees as given in the question. And then times the distance from T1 all the way to the pivot, which is the full length of the plank, so that's just 2 meters. We've completed our 3 torques. We can set this equal to 0. The rest is just algebra. So let's do negative 700 times the sine of 90 times 0.5. That gives us negative 350 Newton meters. Minus, let's do 294 times sine of 90 times 1. That actually will just stay minus 294 newtons. Plus T1 times, let's do sine of 40 degrees times 2. And we'll get 1.29 approximately equals 0. You'll add these two forces to both sides of the equation. So we'll do the same thing over there. They're going to cancel out here. You'll have T1 times 1.29 meters equals, so adding the 350 and the 294 gives you 644 newtons. Excuse me, that would be Newton meters. And then divide both sides by the 1.29 meters. And when you do that, you will get T1 equaling about 501 newtons. So that would be the correct answer for T1. So now that we know that, we can maybe go back to the diagram and just label T1 as 501 newtons. Now let's come up here. It's in equilibrium, the Planck is. So we know that the sum of the forces in the x direction is equal to 0. And we also know that the sum of the forces in the y direction is also equal to 0. Let's go to the y direction first, and we can see that T2 is pointing in the y direction. So this is going to help us find T2. Now, let's kind of highlight all the forces that are acting in the y direction, just so we can see them. We have T2 upward, 700 newtons downward, 294 downward, and then for T1, we have to break it into its components. Now, the x component would point to the right, but for our purposes now, the y component points upward. So we're going to need this y component right there. Notice that that y component is opposite of the 40-degree angle. Because it's opposite, that's the clue that you'll be using the sine to represent that component. So that y component right there is going to be T1 sine of 40 degrees. So here we go. We have the upward T2, so it's positive, minus the downward 700 newtons, minus the downward 294 newtons, and then plus T1 sine of 40 equals 0. Notice that component was positive because it's pointing upward. We can combine all of this, actually. We know T1. We just figured it out. It's 501. So actually, let's do T2 minus 700 minus 294 plus 501 sine of 40 equals 0. Let's combine all that on our calculator. So negative 700 minus 294 plus the 501 sine of 40 gives you minus 672. So you have T2 minus 672 equals 0. Add that over to the other side, and you can see that T2 is 672 newtons. So that's the correct answer for T2. Finally, let's go over to the x direction and just look at those forces. So we'll highlight them. We've got this acting in the x direction, and then the only other force acting in the x direction is the x component of T1. Notice that that is adjacent to the 40-degree angle, so that's going to be T1 cosine of 40 degrees. It's also pointing to the right, so it's positive. T3 points to the left, so it's negative. You'll have negative T3 plus T1 cosine 40 equals 0. Go ahead and fill in the value of T1, which we found was 501 newtons, times cosine 40 equals 0. Let's do the 501 times the cosine of 40. You're going to get 384 approximately. We're running out of room here. Let's come up here. Negative T3 plus 384 newtons equals 0. You can basically just add T3 to the other side, and you would see that T3 is about 384 newtons. So that completes the answers to the question.